Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that feels both simple and impossible. What lies beyond the speed of light? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. So tonight we'll explore what happens when we imagine stepping past nature's greatest boundary, the speed of light. Not with rockets, not with equations, but with calm curiosity, as if we were sitting by a quiet window, watching the stars and wondering what secrets they keep just beyond reach. When you think about limits, maybe you picture a road sign, 50 miles an hour, no faster. A reminder that rules are there, not to be broken, but to keep the flow of life steady and safe. Nature has its own speed limit, though it doesn't come printed on metal signs at the side of the road. It is woven into the very fabric of the universe, the speed of light. Roughly 300,000 kilometers per second, or about 186,000 miles every single tick of the clock. It's a number so vast that it's almost meaningless to everyday life, and yet it shapes every corner of reality. Light from your lamp travelling across your room takes less than a heartbeat to reach the wall. A radio signal sent to the moon arrives in just over a second. But even that gentle delay is a reminder. Light, fast as it is, still takes time. The cosmos moves not instantly, but at this measured pace. A steady cosmic heartbeat that refuses to quicken. Albert Einstein, with his usual mix of curiosity and mischief, realised something extraordinary in 1905. He asked, what happens if you chase a beam of light? If you were fast enough, would it appear still beside you, like a frozen ray? His mathematics, written out with the patient strokes of relativity, answered no. No matter how hard you chase, light will always run ahead at the same speed. Whether you're standing still or on a rocket darting through space, the glow of light moves past you at the same steady pace. It is the great equalizer, the untouchable ruler of speed. And this rule isn't just about brightness, it is about time itself. As something moves faster, closer to the speed of light, time bends and stretches around it. A traveller near light speed would see their own seconds tick slowly, while the universe around them seems to rush forward. Everyday life offers soft echoes of this. Think of a crowded street. People moving quickly, some slowly, yet all weaving in and out of each other's paths. The pace you take changes your perspective of the crowd, but the crowd itself remains. Light as the crowd no one can overtake, the pace no one can surpass. To understand this boundary, physicists often draw a picture called the light cone. Imagine standing in the dark with a lantern in your hand. The beam spreads outward in a cone of brightness, illuminating a patch of ground, the air, the dust motes dancing in the night. That cone marks all the places your light can reach in time. The past lies behind you, the future ahead within that widening cone. Outside it, in the untouched dark, are events that you can never influence, no matter how hard you try. In this way, the speed of light doesn't just limit travel, it shapes causality. What can cause what, and in what order? It can feel frustrating, even unfair, that such a limit exists. We humans are used to breaking limits. We once thought the sound barrier was impenetrable, until airplanes ripped through it with a thunderous boom. But the light barrier is different. Pushing against it doesn't give you a louder boom or a smoother ride. It warps your very sense of space and time. Try to press too hard and physics itself begins to shift beneath your feet. And yet, within this strictness lies a kind of peace. Because light is steady, the universe has order. Stars shine at us across millions of years. Galaxies wheel in patterns we can measure. Even your own eyes in this quiet room depend on light's constancy. Every photon bouncing from the page of a book or the curve of a pillow obeys the same speed, whispering the same law. There's a gentle beauty in knowing that you, me, and every creature that has ever gazed at the stars lives under this same silent rule. We cannot outrun light, and perhaps we're not meant to. But what if, just what if, we could? What doors would open if this universal speed limit could be bent, broken, or simply stepped beyond? Would we glimpse new worlds? Or would we, in trying, unravel the very thread of cause and effect? Tonight, we're going to walk up to that limit, peer over the edge, and wonder. For now, though, let the thought rest lightly, like a lantern glow on your pillow, the speed of light, the quiet pace that shapes the universe. The speed of light may feel like just another big number, like the distance to the moon or the weight of a mountain, but hidden in that number is something deeper. It is not just how fast light travels, it is how reality itself chooses to keep time. And when Einstein uncovered that truth, the universe seemed to tilt ever so slightly on its axis, showing us rules no one had noticed before. Imagine you're watching children play with kites on a breezy afternoon. One child runs fast, the other dawdles, and yet the wind carries the kites with the same invisible hand. That's what light does for us. Whether you stand still, stroll gently, or ride on a rocket darting through the stars, light streams past you at the same speed. It does not bend to your motion. It does not favour one traveller over another. It simply is. This constancy sounds harmless enough, but it carries a quiet revolution. If the speed of light is always the same, then other things must give way. Those other things are space and time. They are no longer fixed backgrounds, like a stage where the play of life unfolds. They are flexible, willing to stretch or compress so that the cosmic speed limit holds true. If you move fast, your time runs a little slower. If you race near light's pace, distances shorten in the direction you travel. It is as if the universe bends itself to preserve light's loyalty. That may sound like abstract mathematics, but the effects are real, measured, and woven into your daily life. The phone in your pocket, relying on signals from satellites overhead, has to account for tiny shifts in time caused by both speed and gravity. Without Einstein's corrections, your GPS would be wrong by miles within minutes. Even when you order takeout or check a map, you are leaning on relativity's hidden generosity. But let's leave the equations aside for a moment. Picture instead a cone of light, the kind you see when a movie projector beams through dust in the air. Physicists call this image a light cone, and it carries the story of cause and effect. Imagine yourself at the tip of the cone, here and now. The widening circle ahead of you is the future your actions can touch. Shine a flashlight, speak a word, drop a pebble in water. Those ripples spread outward, but never faster than light. The shrinking cone behind you is the past, all the events that could have reached you by now. Everything else, the stars whose light has not yet arrived, the distant galaxies whose signals are still on their way, lies outside, unreachable for the moment. The light cone is like the universe's flowchart of possibility. It tells you what can cause what, and in which order. If something sits outside your cone, it cannot affect you yet. If you sit outside mine, I cannot yet hear your story. Light is the messenger that stitches events into order, making sure cause comes before effect, even if the two are separated by 100 million years. Einstein's insight was that this wasn't just a convenient picture, it was the architecture of space-time itself. Every event, your breath, a leaf falling, a star collapsing, sits in this network of cones, and all the cones are tilted, stretched, and arranged so that nothing outruns light. Without that structure, causality itself would fray. A letter might arrive before it is sent, a knock might come before the hand lifts, a life might unfold before a birth. There's something almost comforting about this cosmic discipline. It means the universe plays fair. Messages arrive after they're written. Causes precede their effects. It is not a chaotic jumble of scrambled timelines, but a calm, steady unfolding. When you sip tea, you know the water boiled first. When you read a sentence, you know the letters were typed before your eyes received them, all because light refuses to yield its crown. Still, humans are dreamers, and whenever we meet a rule, we wonder what lies beyond it. We have broken barriers before. The sound barrier once seemed absolute until pilots roared through it in planes that shook the sky. Why should light be any different? If the universe insists that nothing can go faster, we feel a tug of curiosity, a whisper of rebellion. What would happen if we could? This curiosity is not dangerous. It is the spark that drives science forward. But before we leap ahead into impossible speeds and paradoxes, it's worth pausing here, at the edge of the cone. Take a breath and imagine yourself as a single point of light, sending ripples outward into the dark. Those ripples carry your story. They can travel far, but never instantly. They need time. And in that gentle pace lies the reason reality makes sense. As we continue, we will begin to tug at this boundary. What if a signal, or an object, or perhaps a strange kind of particle could outrun the cone? What would that mean for order, for memory, for the quiet unfolding of time? For now, let this thought linger like a lantern flicker in your mind. The universe has rules, and light sets them. Whether those rules can ever bend is a question we'll drift into next. It's in our nature to wonder what lies beyond every fence, every horizon, every line of paint across a road. Limits invite curiosity. The speed of light, so steady and immovable, is perhaps the grandest of these boundaries. And so we ask, softly but persistently, what if we broke it? Imagine you're standing on a quiet hill at night, holding a flashlight. You sweep the beam across the landscape. In that instant, the patch of light on a far-off mountain can appear to move faster than light itself. One moment it shines on a tree nearby, the next on a peak miles away. The spot seems to leap across the distance in no time at all. Of course, nothing physical has outrun the photons. The beam is just arriving at different points in sequence. Still, it gives us a taste of how tempting it is to imagine faster-than-light motion. Now, take a different scene. You shout across a canyon and wait for the echo. The sound takes time to return, delayed by the air's limited speed. What if your voice could race ahead faster than sound, reaching the rocks and bouncing back instantly? It would feel magical, like the world answering you before you'd finished asking. Replace sound with light, and you begin to see the lure of imagining signals that leap across space instantly, or even backwards. Science often begins with such gentle what-ifs. What if we could travel so fast that time itself reversed? What if a message could be sent not just across the stars but back into yesterday? At first, these questions seem playful, like riddles whispered at a campfire. But when Einstein's equations are stretched to include faster-than-light travel, the playfulness turns serious. The math suggests something startling. If you can move faster than light, then in some frames of reference you can move backwards in time. That sounds like science fiction, and indeed it is the soil from which many stories grow. But it's also embedded in the logic of relativity. Imagine two observers. Let's call them Mira and Leo. Mira is on Earth. Leo is on a spaceship travelling close to the speed of light. If Mira could send a signal to Leo that somehow moved faster than light, relativity predicts that Leo might receive it before Mira had even pressed the button. In Leo's frame, the cause and effect would swap places. The letter arrives before it is written. This is where paradoxes begin to creep in, quiet but persistent. If you can receive a message before it is sent, you might change what the sender decides to write. If you can travel back before your own departure, you might alter the very conditions that allowed you to leave. These puzzles, known collectively as causality violations, are more than headaches for philosophers. They threaten the basic logic that makes the universe intelligible. But let's not rush too fast into knots of logic. Instead, think of something familiar. Dominoes. Set them up in a long chain across a room. Tap the first and the cascade begins one after another falling in order. That order is comforting, predictable. Now imagine if one of the dominoes halfway down the line suddenly toppled before its neighbours. The rhythm breaks. Did it fall on its own? Did some unseen hand intervene? The chain no longer makes sense. Faster than light motion threatens to do the same for the dominoes of reality. And yet, the temptation remains. If we could only step past the barrier, the cosmos would open like a book without end. Distances that take light years could shrink to minutes. A signal to a distant colony could return instantly. Journeys that stretch beyond lifetimes could become evening trips. The dream is so alluring that it fuels not only stories and films, but serious scientific speculation. It's important to pause and notice the duality here. On one side, the promise of freedom, to leap the stars, to cheat delay, to escape the patience light demands of us. On the other side, the warning, to do so may unravel the very thread of cause and effect. To imagine faster than light travel is to imagine walking a tightrope strung between wonder and contradiction. So, what happens if we lean into that wonder a little more? We'll meet ideas like tachyons, particles that, in theory, can only exist beyond the speed of light. We'll consider warp bubbles that carry space itself faster than light, avoiding the rules rather than breaking them. And we'll touch on quantum whispers, like entanglement, that seem instantaneous, but hide their own subtle limits. For now, hold this thought gently. Every barrier invites dreaming, and the speed of light is no different. The universe may whisper no, but our imaginations answer what if. And sometimes, that quiet rebellion is the beginning of discovery. Think for a moment about your daily rhythm. You boil water, then pour tea. You write a letter, then send it. You take a step, and only then does the ground meet your foot. Life makes sense because the order of things is steady. Cause comes first, effect follows. It is so ordinary we rarely notice it, like the steady background hum of a refrigerator, always there, unremarkable, yet essential. But when we imagine moving faster than light, the hum falters. The sequence begins to wobble. Suddenly, it is not so clear whether the letter was sent before it was received, or whether the tea boiled before it was poured. Faster than light motion, in the language of physics, doesn't just stretch time, it can flip it. It can make effect slip ahead of cause, like a story read backward, or a song whose ending plays before the opening note. One of the clearest ways this puzzle appears is through the famous grandfather paradox. It's often told dramatically. Suppose you could travel into the past and prevent your own grandfather from meeting your grandmother. If they never met, you would never be born. And if you were never born, how could you have travelled back in the first place? The loop eats its own tail, leaving no clear way forward. Now, most of us are not planning to meddle with family trees across time, but even in smaller ways the paradox holds. If you send a faster-than-light message to a friend, relativity suggests that in their frame of reference, they could receive it before you sent it. And once they have that knowledge, they could change what you decide to write. The chain of cause and effect twists into knots. It may sound like a riddle dreamed up at a sleepover, but the mathematics of relativity says it isn't just fantasy. It is a logical consequence of trying to cross light's barrier. When events are close together in time and space, observers usually agree on their order. But if something could leap faster than light, different observers could disagree completely. One might see the glass shatter first, another might insist the stone was thrown first. Both views would be valid in their own frames. To soften this idea, imagine a pair of postcards. You write one, stamp it, and send it by post. Your friend receives it days later. All makes sense. Now suppose in some strange town the postal service could deliver a card before it was written. Your friend opens the envelope, reads your words, and then phones you. Startled, you decide not to write the card after all. Yet there it is, already delivered. The logic collapses. This is what faster-than-light motion threatens. Not just inconvenience, but the very structure of reality that lets one moment lean on another. Without that structure, stories unravel. A child might grow before being born. A sunrise might glow before night has ended. Of course, some philosophers and scientists have tried to imagine ways out. Perhaps the universe has hidden rules that prevent paradoxes from forming. Maybe, if you tried to send a message into the past, some small detail would always intervene. The machine fails, the signal distorts, or the recipient never quite understands. This idea is called the Novikov self-consistency principle, a mouthful that simply means whatever happens must be consistent. The universe won't allow contradictions. Others prefer to imagine branching paths. Instead of a single line of cause and effect, the universe splits whenever a paradox threatens. If you change the past, you create a new timeline, leaving your own untouched. In this view, there is no contradiction, just an ever-expanding tree of possibilities. But for many physicists, these are imaginative patches rather than solutions. The simplest explanation may be that the universe has set the speed of light as a boundary, precisely to prevent these tangles. The cosmic traffic law keeps us safe from colliding with our own past. Still, paradoxes are not only traps, they are invitations. By pointing out where logic collapses, they shine a light on what we do not yet understand. They push us to ask, is causality as rigid as it seems? Or is there some deeper order hidden beneath the confusion? As you rest here, you might feel a little dizzy at the thought of time folding in on itself. That's natural. Let it be like the sensation of standing at the edge of a funhouse mirror, watching your reflection bend and ripple. Strange, perhaps unsettling, but also fascinating. Because the truth is, while paradoxes warn us of the dangers of faster-than-light travel, they also keep our imaginations alive. They remind us that the universe is not simple, not easily caged in logic. It is a place where even the most basic rule, cause before effect, can be questioned. And in that questioning lies the heart of science. Wonder, curiosity, and the willingness to follow an idea even when it twists into loops. So tonight, as you drift a little deeper into this story, hold on to the image of postcards arriving before they're written, or dominoes falling out of order. These are the gentle riddles that faster-than-light dreams bring. In the next part of our journey, we'll lean even closer and ask, if such paradoxes are possible, what does that mean for how we see the past and the future? Could faster-than-light motion give us glimpses of what has already happened, or even of what is yet to come? Look up at the night sky, and you're already gazing into the past. The twinkle of a star might be light that set off long before humans built cities, or even before our species existed at all. Some of the starlight reaching your eyes tonight began its journey when mammoths roamed the earth, when the oceans lapped against different shores, when entire civilizations had not yet been imagined. Every glance at the heavens is a quiet kind of time travel, a reminder that light carries stories but needs time to deliver them. That delay is why the speed of light is more than just a number. It sets how much of the universe we can know at any moment. Galaxies billions of light years away are also billions of years in the past, their current selves hidden from us until their new light arrives. The light cone we spoke of earlier doesn't just shape causality, it shapes our knowledge. It places a veil over the present, letting us peek only into histories written long ago. But what if we could lift that veil? Imagine if a message could outrun light. Suddenly the lag would vanish. We wouldn't just see ancient starlight. We could, in principle, watch a star as it is right now, not as it was eons ago. The universe would change from a collection of old photographs into a live broadcast. The past, which currently streams to us in slow motion, would come rushing in all at once. The idea is breathtaking, but it also bends logic in peculiar ways. Suppose you could send such a faster-than-light signal back to Earth from a distant star. Depending on the observer's frame of reference, that signal might arrive before it was sent. In effect, you could call home yesterday, delivering news before it had happened. The conversation could loop into paradox. Don't board the ship tomorrow, something goes wrong. And if the warning is heeded, the signal itself would have no reason to exist. Everyday life gives us soft metaphors for this. Think of writing in your diary. Normally today's entry follows yesterday's, a neat chain of memory. Now picture opening the book and finding tomorrow's page already filled in, written in your own hand, yet describing things you have not lived through. Would you believe it? Could you resist reading ahead? And what would it mean for the choices you think are yours to make? In the language of physics, this is the slippery slope of superluminal travel. To move faster than light is not just to move quickly, it is to step outside the order that tethers past to future. And once outside, the distinction between the two blurs. The universe no longer guarantees which came first. But there's a gentler way to hold this thought. Imagine standing at a river's edge, watching the current sweep past. Normally the water carries leaves downstream, one after another. If somehow a leaf could dart upstream faster than the current, it would surprise you, arriving before it ever left your view. That is what faster-than-light motion would be like. The current of time reversed, leaves arriving out of order. Strange, yes, but the river would still flow. The scene would still be beautiful, even if confusing. Philosophers sometimes describe this possibility as causal glimpses. Perhaps if tachyonic signals existed, they might not let us change events but only view them, like a window into yesterday or tomorrow that cannot be touched, only observed. In such a world, destiny and choice would sit uneasily together. Would you live more cautiously if you could see tomorrow's accidents? Or would you live more freely knowing that outcomes are already written? Science fiction often plays with these ideas because they strike at something very human, our yearning to know what lies ahead and our longing to revisit what we've lost. Faster-than-light dreams become metaphors for grief, for hope, for curiosity. They whisper that maybe, just maybe, distance and time are not as final as they appear. Of course, real physics warns us that such windows may never exist. The strictness of relativity, the safety of causality, seems designed to keep us from collapsing into contradiction. Yet even the impossibility is meaningful. By wondering what it would mean to see the past directly, or to touch tomorrow early, we sharpen our understanding of why the universe protects its order so carefully. So tonight, as you settle deeper into stillness, imagine yourself at the center of your own light cone. Past events drift toward you, gentle waves on a pond. Future ripples spread outward, awaiting your actions. And somewhere beyond that cone, in the quiet darkness, lies the forbidden dream. To reach across time, to see not just what was, but what will be. Hold the thought gently, like holding a page of your diary yet to be written. Tomorrow will come soon enough, carried faithfully by the light, and in that patient unfolding lies the story of the universe itself. Every so often in science, an idea comes along that feels less like a discovery and more like a whisper from the edges of imagination. Tachyons belong to this category. They are not particles we have measured in laboratories, nor visitors we have caught in detectors. They are instead possibilities written in mathematics, faint outlines of what might exist if the universe dared to stretch its own rules. The story begins in 1967 with a physicist named Gerald Feinberg. Now at the time, relativity had long since crowned light as the fastest traveller in existence. But Feinberg wondered, what if the equations that describe particles could allow for another kind of being? one that is not slower than light, or even at light speed, but forever faster. He gave them a name derived from the Greek word tachys, meaning swift. Tachyons, the swift ones. The rules for tachyons are strange right from the start. Unlike ordinary matter, which begins at rest and can accelerate but never quite reach light speed, tachyons can never slow down below it. They live entirely on the far side of the cosmic boundary, always faster, always out of reach. If ordinary particles are like hikers who begin at the foot of a mountain and climb upward with effort, tachyons are like strange climbers who can only run downhill, forever unable to stop at the summit. It's hard to picture such a thing because our entire experience is built on the familiar. We know what it feels like to rest, to walk, to run. The tachyon has no resting state. It cannot pause, cannot sit quietly on a chair, cannot move slowly enough to be still in our world. It is motion made permanent, a traveller that cannot visit the quiet pace where most of the universe resides. And yet, in the gentle lines of mathematics, tachyons fit surprisingly well. Relativity's equations leave space for them, as though the universe left a door half open for creatures of perpetual swiftness. Their behaviour would not break the structure outright, but it would make that structure shimmer with paradox. A tachyon racing between 2 points might arrive before it set out. To some observers, the signal would move forward. To others, it would run backward. Everyday life can give us faint metaphors. Think of a ball rolling down a hill. The higher it begins, the more energy it has to spend. But once it's rolling, it cannot stop midway unless some force intervenes. If tachyons existed, they would be like balls that could never roll uphill into the region of ordinary particles. Their entire world is on the downhill slope, forever rushing, never at rest. Another anchor might be found in stories of travellers who never return home. Imagine a ship that sets sail but cannot enter the harbour again. It moves only from one distant port to another, always arriving before the signal of its departure can catch up. This is how tachyons invite us to think, not as matter we can touch, but as possibilities that redefine what before and after might mean. For many physicists, tachyons became less a prediction and more a thought experiment. If such particles could exist, what would they teach us about time, causality, and the hidden limits of nature? Could they be used as messengers carrying information across the cosmos faster than light's patient pace? Or would they forever resist capture, slip in between definitions the way a shadow slips between rays of light? We have searched in small ways. High-energy experiments have looked for hints of particles behaving tachyonically, strange signals arriving earlier than expected, disturbances moving too quickly through detectors. None have been confirmed. The swift ones remain, for now, residents of imagination. And yet, imagination is not trivial. It is a seed from which progress grows. By naming tachyons, Feinberg invited us to wonder about what lies beyond the limit. He handed us a metaphorical telescope, not pointed at the stars but at the boundary of physics itself. So, as you lie back and let your thoughts drift, picture these unseen travellers. Not glowing streaks or fireballs, but subtle presences, forever faster than light, unable to cross into our slower world. They are like runners in a race we can never join, their track forever on the far side of possibility. We cannot catch them, but we can dream of them, and perhaps that is enough. Because in the act of dreaming, we stretch ourselves closer to understanding, closer to asking the questions that matter. Why does the universe have a speed limit? Is it absolute or merely a rule we have yet to understand fully? The tachyons whisper that maybe, just maybe, the story of speed and time is not complete, and if so, then the universe still holds surprises, waiting patiently just beyond the reach of light. Numbers can sometimes feel like strangers who speak in riddles. Most of the time, they behave politely. 2 + 2 makes 4. A triangle's angles add to 180 degrees. But every so often, mathematics steps into territory that feels dreamlike. One of those moments arrives with tachyons because to describe them properly, the equations ask for something unusual: imaginary mass. Now, the word imaginary might sound dismissive, as though it means pretend, like a childhood tea party with invisible guests. But in mathematics, imaginary numbers are as real, ironically enough, as any other. They are numbers that involve the square root of -1, a quantity we cannot place on the ordinary number line, but that proves astonishingly useful. Electrical engineers rely on it every day. Quantum mechanics is woven from it. In this sense, imaginary is less a synonym for fake and more a reminder that our intuition lags behind. For tachyons, the math suggests their mass would have to be imaginary to make the equations consistent. Instead of weighing something in kilograms, you end up with a number involving that peculiar square root. And what does that mean for their behaviour? Here is where things grow strange. For normal matter, stones, trees, people, the faster you go, the more energy you need to push yourself close to light speed. The equations tell us that as you approach c, your energy requirements shoot upward toward infinity. That is why no rocket, no matter how powerful, can ever push ordinary matter past light's pace. It would require an infinite supply of fuel. Tachyons with their imaginary mass flip this logic upside down. The faster they go, the less energy they need. Paradoxically, if you tried to slow a tachyon down toward light speed, you would have to pour in more and more energy. The cosmic limit is a one-way mirror. On our side, ordinary matter slows as it nears it. On the other, tachyons resist slowing down, forever barred from entering the slower world. It's a difficult idea to hold, so let's soften it with imagery. Picture a river. Normally, if you build a dam, the water piles up behind it with more force. Restricting the flow increases pressure, but imagine a river that does the opposite. The more you dam it, the weaker the water grows, and when you finally release it, it flows stronger the less you try to contain it. That is the tachyonic paradox. Effort in the wrong direction seems to weaken rather than strengthen. Or think of climbing a hill. For ordinary particles, the hill is steep as they approach light speed. Each step requires more energy, more effort, until progress becomes impossible. For tachyons, the hill is inverted. To slow down toward the summit is to fight against infinity. They can only tumble further down the slope, moving faster with less effort, forever kept away from the top. This reversal is one reason tachyons remain in the realm of speculation. While the math works neatly, the implications feel deeply alien. How would you ever catch or measure something that slips away more easily the more you try to restrain it? Even in thought experiments, they behave like shadows of logic, always present but never graspable. And yet, there is beauty here too. Imaginary mass is not just a quirk, it is a doorway into new ways of thinking. Physics often advances by confronting ideas that feel absurd at first. Negative numbers once seemed impossible. You cannot have negative sheep in a pasture, and yet negative values are indispensable for bookkeeping, for algebra, for understanding debts and losses. In the same way, imaginary numbers seemed useless until they became the backbone of electricity and quantum theory. Perhaps tachyons, with their imaginary mass, are simply another whisper that what feels impossible today may be tomorrow's foundation. It is worth remembering that much of science is about translation. Equations are one language, dense and precise. Stories and metaphors are another, softer and more accessible. When we translate imaginary mass into rivers that weaken under dams or hills that flip upside down, we are not trivializing it. We are bridging the gap between our world of experience and the universe's stranger grammar. So, let your mind drift with this paradox. A particle that needs less energy the faster it goes. A runner who finds the road easier the more they sprint. A river that flows stronger the less you try to contain it. It is not how our world works, but it may be how some other corner of reality whispers its rules. And if such particles exist, they are not merely curiosities. They are ambassadors from a realm where the boundaries of mass, energy and speed are drawn differently. To imagine them is to glimpse an alternate version of physics, one that humbles us with its oddness and charms us with its possibilities. For now, though, it is enough to marvel at the strangeness itself. A universe that allows us to write down the mathematics of tachyons is already generous in mystery. Whether the swift ones exist or not, they invite us to dream of a reality where slowing down is impossible, and where speed is not a burden, but a release. So far, tachyons have lived mostly in our equations and our daydreams. But what if they were not just whispers of mathematics? What if, in some subtle way, they brushed against our world? How would we notice them? What would it feel like to live in a universe where the swift ones occasionally left footprints? To answer gently, we should start with light itself. When ordinary particles move faster than light in a medium, say water or glass, they produce a peculiar glow called Cherenkov radiation. If you have ever seen the haunting blue shimmer inside photographs of nuclear reactors, that is the light of particles outrunning light's pace within that medium. Not in a vacuum, but in a slowed down arena where light crawls more sluggishly. It's the visual equivalent of a sonic boom, a sudden flare announcing that something has broken through a local barrier. If tachyons existed, some physicists once imagined they might leave similar signs, a kind of superluminal glow like space's own neon nightlight. Instead of thunderclaps or shock waves, they might announce themselves with flashes of unexpected energy, signals that arrive before their sources, or disturbances that seem to ripple backward. It is a playful thought because the imagery is so vivid. Picture sitting in a quiet room when suddenly the lamp glows brighter a second before you switch it on. Or watching raindrops fall upward, hitting the sky before leaving the ground. Tachyons, in theory, could play such tricks, at least in the way their signals ripple across frames of reference. But here we must tread carefully, because physics is cautious. While the mathematics allows tachyons, actual evidence is nowhere to be found. We have built detectors that can register the faintest glimmers of neutrinos, particles that ghost through the Earth like whispers through walls. We have captured gravitational waves stretching space itself by less than the width of an atom. Yet tachyons remain invisible, silent, and absent. If they do exist, they are masters of disguise. And perhaps that's the point. If tachyons were real, they would not interact with matter in ways we're used to. They would skim along the edges, too swift to leave much trace. Imagine trying to grab a shadow with your hand. The faster you chase, the more it slips away. A tachyon in our detectors might be like that, present, but always dodging our grasp. Still, it's worth entertaining the what if. What if tachyons could carry signals? Suddenly, communication would leap across the cosmos with no delay. Astronauts on Mars could phone home without the patient pause of minutes-long light lag. A message could be exchanged instantly across the galaxy. Some speculations go further. Tachyon signals might even carry information into the past, letting us glimpse yesterday's choices or tomorrow's news. And here, the paradoxes return, slipping quietly back into the story. If you can send a message back, do you risk erasing the reason you sent it? Could a warning from tomorrow prevent the accident that caused the warning? The loops become dizzying. It's like writing yourself a note that arrives on your desk before you pick up the pen. A useful trick, perhaps, but also a dangerous one for logic itself. Let's step away from the paradoxes and enjoy the imagery instead. Picture a city at night, every building strung with neon lights. Now imagine one of those lights flickers not forward in time but backward, glowing slightly before the switch is flipped. The city remains beautiful, but uncanny. That is how tachyons might touch our world, not with chaos, but with subtle hints that time's arrow is not as strict as it seems, and yet there is humour here too. If tachyons were real, they might be nothing more than the universe's pranksters, making lamps flicker early or signals arrive out of order. Perhaps the blue glow in reactors would be their calling card. a cheeky reminder that physics has more tricks up its sleeve than we realise. Like mischievous night lights, they would keep us guessing, never letting us be entirely sure whether the story we are watching is playing forward or backward. For now though, tachyons remain elusive. Their absence in experiments is as telling as their presence in equations. The universe, as far as we can measure, remains steadfast in its loyalty to light's boundary. But that does not make the thought of tachyons useless. On the contrary, they sharpen our curiosity. By wondering what it would mean for such particles to exist, we better understand why the laws are written the way they are. So let your mind wander with this gentle what if. Imagine blue glows shimmering in empty space, signals that race ahead of their own causes, and cosmic pranksters forever too swift to catch. Even if tachyons never touch our world, the dream of them has already touched us, reminding us that physics is not just about what is, but also about what might be. Laws are meant to give order. Traffic lights, recipes, the steps of a familiar routine, all exist so that life unfolds smoothly. You boil the pasta first, then add sauce. You stop at red, go at green. Physics too has its traffic laws. The speed of light is one of the most important, the unblinking red light at the edge of possibility. But tachyons, if they existed, would run that red light every moment of their existence. They would not only cross the boundary but live beyond it, forcing us to ask whether our rulebook is as complete as we believe. Imagine waking up one morning to find every road sign in your city quietly rewritten overnight. The speed limits are strange numbers you don't recognise, the directions point somewhere else, and the rules no longer match the roads you know. Confusing, yes, but also strangely exhilarating. That is what tachyons would do to our physics. The familiar signs of relativity, cause before effect, light as the fastest messenger, would have to be revised. At its heart, relativity is built on a simple promise that no information, no particle, no influence can move faster than light in a vacuum. Remove that promise, and many of the structures we rely on begin to wobble. Time becomes less a straight arrow and more a tangled ribbon. Simultaneity, the idea that two events happen at the same time, that becomes slippery. And causality, the cornerstone of all reasoning, begins to look less like a wall and more like a curtain that can be pulled aside. Physicists have long known this. That's why, whenever tachyons appear in the mathematics, the alarms of paradox ring softly in the background. To admit their existence is to admit that effects might precede causes, that the story of the universe might be written in loops rather than lines. And yet, there is also a thrill here. Every time science has faced apparent contradictions, the resolution has opened a new frontier. Once, Newton's laws seemed absolute, until Einstein revealed a deeper layer in relativity. Once, the smooth world of classical physics seemed complete, until quantum mechanics added its shimmer of probability. Tachyons might, in this sense, be invitations, gentle nudges telling us that our understanding of space-time is not the final draft. How would the universe look if tachyons were confirmed? For one, we would need to redefine communication. Perhaps signals could travel instantaneously, bridging galaxies without delay. Perhaps energy itself could be transmitted in ways that ignore distance. And perhaps our maps of time would need to be redrawn, with arrows pointing not just forward, but curling into strange loops. This isn't to say that the old rules would be discarded entirely. Just as Newton's laws remain excellent for everyday engineering, relativity would still describe most of the universe beautifully. But above that, layered like a new dimension of music over a familiar melody, would be the tachyonic rules. The laws we thought unyielding would reveal themselves as approximations, like a recipe that works in most kitchens but hides a secret ingredient waiting to be discovered. Of course, for now, this is all speculation. The speed of light has held firm through every experiment, every observation. We have measured particles hurtling through accelerators, watched photons from distant galaxies, tracked gravitational waves rippling across the cosmos, and always, light's boundary remains intact. Tachyons live only in the margins, never in the data. But speculation has its own role to play. By imagining what laws might break, we learn why they matter. By picturing the universe with tachyons, we see more clearly why relativity's order is so comforting. It's like rehearsing what would happen if the traffic lights all went dark. You gain a deeper appreciation for their steady glow when you drive home at night. So let your thoughts wander gently to a universe rewritten. The road signs are unfamiliar, the laws are less strict. Messages slip ahead of themselves, the past and future blur. It is strange, yes, but also beautiful. A reminder that reality, even when we think we have mapped it, may still hold entire continents of the unknown. And as you drift in that thought, remember, science is not a fortress of certainty but a garden of growing ideas. Tachyons may never exist, but the act of imagining them keeps the soil fertile, ready for whatever new seeds the cosmos offers us next. When you look up at the night sky, there's a quiet ache in the distance. Those stars are so close to our eyes, twinkling in the darkness, yet unimaginably far away in truth. The nearest one beyond our sun, Proxima Centauri, sits more than 4 light-years away. That means even at light speed, a pace no spacecraft of ours has ever reached, it would still take over 4 years just to arrive. For galaxies farther out, the numbers stretch into millions, even billions of years. The cosmos is vast and light is fast, but together they create a wall of waiting. Now imagine if that wall could be lowered, even just a little. Suppose tachyons or some other faster-than-light trick could let us step across the gulf as easily as crossing a room. Suddenly, the dream of interstellar travel would no longer be a fantasy whispered in science fiction. It would be an itinerary, a calendar entry, a ticket you could book. It helps to bring this down to earth with a simple picture. Think of walking home after a long day. The road winds and twists, and though your house is just across the park, you must follow the path. It takes time, but then you notice a gate standing open, and you cut straight across the grass. In an instant, your journey is shorter, not because your legs move faster, but because the route is bent in your favour. This is how physicists describe some FTL concepts. Not a reckless sprint through space, but a clever folding of the map itself. One of the most famous of these foldings is the Alcubierre drive, a solution of Einstein's equations proposed in the 1990s. It imagines a bubble of space-time that contracts in front of a spacecraft and expands behind it, carrying the craft forward without ever locally exceeding the speed of light. The ship itself doesn't break the law, the space around it does the moving. It's like standing on a moving walkway at the airport. Your legs may walk slowly, but the floor itself carries you further. If tachyons were real, they might serve as signals that whisper between stars instantly. Communication could leap across the void without delay. No more waiting 20 minutes for a radio signal to reach Mars and another 20 for the reply. Instead, astronauts and mission control could speak as though they were in the same room. In theory, such signals might stretch all the way across the galaxy, letting civilization stay in touch despite the distances that currently silence them. But travel, real journeys of bodies across the stars, would be the true revolution. Entire generations of science fiction have dreamed of it. A trip to a distant planet could take hours instead of centuries. A voyage to another galaxy might be a holiday adventure rather than a lifelong exile. The loneliness of space, the vast gulfs that keep us bound to our single blue planet, would dissolve. Of course, there are catches. The Alcubierre drive, as elegant as it sounds, requires exotic matter with negative energy density. Something we have never observed and perhaps never can. Tachyons too remain theoretical, more whispers than particles. And even if they existed, using them as engines or messengers might prove impossible. It's one thing to dream of cutting across the park. It's another to build a path that doesn't collapse beneath your feet. Still, there is value in the dreaming. Every great journey begins not with engines, but with imagination. The first sailors who crossed oceans had only stars and courage to guide them. The first astronauts had rockets that barely looked capable of leaving the atmosphere. Yet they went, and by going, they turned impossibility into history. Perhaps the same will be true for journeys beyond the speed of light. Let's pause and soften this with a bedtime image. Imagine lying in your bed tonight, but instead of closing your eyes, you find yourself drifting upward, gently, through the ceiling and into the sky. You rise past clouds, past the shimmer of the atmosphere, until the earth curves below you like a glowing marble. Then, without effort, you slip across the dark, past planets and stars, as easily as turning a page in a book. In this dream, distance has no hold. The universe opens like a garden, each flower a star you can lean down to smell. That is what faster-than-light travel promises us in imagination. Not just technology, but intimacy with the cosmos. It transforms space from an unreachable canvas into a walkable meadow. Whether tachyons ever carry us there or not, the act of imagining the journey is itself a kind of exploration. So as we drift deeper into the story, let yourself wonder, what would it mean to live in a world where the stars were not far but near, where the galaxy was not a distant dream but a neighbourhood, where every night sky was not just a view but a map waiting for footsteps? Every law of nature we've explored so far has shaped not just our science, but our sense of order. Gravity pulls us down, so we plant our feet on the ground. The sun rises, so we mark our days. Light sets a limit, so we measure journeys by the time it takes to arrive. All of these quiet rules create a rhythm we can trust. But imagine, for a moment, that tachyons were real. Imagine signals arriving before they were sent, or events unfolding before their causes. The rhythm begins to falter. The melody of cause and effect drifts into something stranger. And within that strangeness arises a question as old as philosophy itself. If time can loop, if effect can precede cause, what happens to free will? Think of something simple, sending a message. You type a note to a friend, press send, and wait for the reply. Now imagine that in a tachyon-filled world, the reply arrives before you type your message. You open your inbox, and there it is. Your friend's answer to a question you haven't asked yet. Do you still have the freedom to choose what to write? Or has the choice already been made for you? It's a thought experiment that feels like a riddle. Free will depends on the assumption that the future is not fixed, that your decision now shapes what comes next. But if information can flow backward, then tomorrow may already be written, and your role becomes not author but actor, following a script handed to you in advance. Some thinkers soften this paradox with the idea of self-consistency. Perhaps whatever you choose, it will always align with what the message already shows. If the reply says yes, then you are always destined to ask a yes question. You cannot break the loop, because the loop is the universe's way of stitching time together without contradiction. In this picture, free will is less about choice and more about harmony. Your decisions flowing like notes in a song that has already been composed, even if you only hear it one measure at a time. Others take a different view, imagining branching realities. If tachyons allow effects to spill into causes, then each paradox splits the universe into a new path. In one branch, you ask the question. In another, you don't. Both unfold, each consistent in its own way, but separate from one another. Free will, then, is preserved, but not in a single timeline. Instead, it becomes a garden of forking paths, every choice a new world. These are dizzying ideas, and yet they touch something tender in us. We want to believe our choices matter, that the tea we brew, the words we say, the steps we take shape the future in ways no one else can predict. The thought that tachyons might blur this order is both thrilling and unsettling. To bring it closer to Earth, think of reading a book. Normally you turn the pages in sequence, one after another. The story flows from beginning to middle to end. Now picture a copy where some pages are printed out of order. You read a conversation before you know the question. You encounter a farewell before the meeting. Does that ruin the story? Or does it simply make the experience stranger, more layered, like a dream where events drift out of sequence but still carry meaning? A tachyon universe might feel like that, confusing but not empty of purpose. Free will might not vanish, but it could take on a new shape. Instead of forging a future from scratch, perhaps we would be discovering a path already written, or choosing which branch to inhabit. And here lies the quiet beauty. Whether free will is absolute or entangled in loops, the act of living still feels the same. You still taste your tea, still laugh with friends, still wonder at the stars. Your experience remains vivid, even if the script was written in ways you cannot see. In fact, the very act of asking, "Do I have free will?" may itself be part of the loop, evidence that questioning is woven into the design. So let this thought rest softly in your mind. Tachyons challenge not just physics, but philosophy. They remind us that free will and destiny may not be opposites at all, but partners in a dance too complex for us to see from the floor. From above, perhaps the dance is already choreographed. From within, it feels like improvisation. Both can be true at once, and as you close your eyes tonight, imagine your life not as a straight arrow, but as a ribbon, curling and looping, doubling back on itself in graceful arcs. You walk along it, one step at a time, never sure what comes next. But the ribbon itself is beautiful, whether woven by choice, destiny, or both. There's a quiet comfort in shortcuts. You take a familiar road home, winding and slow, until one day you notice a small alley, a gate through the park, a path across the grass. Suddenly the distance shrinks. You arrive sooner, not because your legs move faster, but because the map itself has bent in your favour. Physicists sometimes dream of shortcuts on a cosmic scale. If we cannot outrun light, perhaps we can persuade space itself to lend us a hand. Instead of racing across the stars, what if we could fold the space between them? This idea took shape in 1994, when physicist Miguel Alcubierre discovered a peculiar solution to Einstein's equations of general relativity. Those equations describe space-time not as a rigid stage, but as a flexible fabric, able to stretch, bend, and ripple under the weight of mass and energy. Alcubierre asked, could that fabric be shaped into a bubble, one that carries a spacecraft like a raft on a current? The answer, at least in mathematics, was yes. Imagine placing your ship inside a bubble of space-time. In front of you, the fabric contracts. Behind you, it expands. The bubble itself surfs along this wave, carrying you forward without the ship ever locally exceeding the speed of light. From inside, it feels calm. Your clocks tick normally, your teacup sits still on the table, yet to an outside observer, you've crossed a gulf faster than light could in ordinary space. The metaphor often given is that of an ant on a blanket. Normally the ant must crawl across the cloth, step by step. But if you pinch the blanket so that 2 points touch, the ant can simply walk across the fold. The distance hasn't vanished, it's just been rearranged. It sounds almost too good to be true, and in a sense it is. The mathematics of Alcubierre's bubble require something called negative energy, a form of matter we have never observed. Ordinary matter, even in stars or black holes, curves space-time in one direction. To create the warp, you'd need matter that curves it the other way, like trying to inflate a sail with wind that blows backward. The amounts required, according to early calculations, were astronomical, more than the mass of entire galaxies. Later refinements reduced the estimate, but it still remains far beyond anything we can produce. Still, the beauty of the idea lies not in its practicality, but in its imagination. It shows that within the rules of relativity, the very theory that forbids faster than light motion, there are loopholes hidden like quiet paths in the woods. The law is not broken, but bent. The cosmic traffic sign still reads no speeding, but clever travellers find that if you move the road itself, you can arrive sooner without ever breaking the rule. In a way, this mirrors how we live our own lives. Sometimes progress comes not from running harder, but from rearranging the path. You might struggle with a problem until a new perspective folds it neatly, revealing an answer that was always nearby. The warp bubble is a cosmic version of this, not faster footsteps, but a folded map. Of course, the imagery also invites wonder. Picture a small ship, humming quietly in the dark, wrapped in a shimmering bubble of distorted space-time. From the outside, stars stretch and bend around it, their light warped into halos. From the inside, the crew feels nothing at all, no motion, no acceleration, just the calm ticking of their watches as the universe slides past. It is a bedtime dream of travel, effortless, silent, serene. But perhaps the most valuable part of the Alcubierre drive is not whether it will ever exist, but what it represents. It shows us that even our most rigid laws may hide creativity. Einstein's equations, which so firmly guard the speed of light, also whisper of ways to play within the rules, like children discovering secret passages in a familiar house. So, as you rest, imagine stretching a blanket across your bed. Place a toy at one end and pinch the fabric so the toy slides closer to your hand. This simple gesture is, in spirit, what warp bubbles promise. A universe where distance is negotiable, where the stars are closer than they seem, not by speed, but by softness of space itself. For now, it remains a dream, a sketch on the blackboard of imagination. But in dreaming of it, we remind ourselves that the universe is not closed off. It is pliable, surprising, and perhaps in ways we do not yet understand, willing to meet us halfway. Sometimes the universe hides its mysteries not in blazing fireworks, but in quiet whispers. Quantum entanglement is one of those whispers, a phenomenon so subtle, so elusive, that it seems more like a magician's sleight of hand than a law of physics. And yet, it is as real as the moonlight that slips through your window at night. The story begins with particles, tiny specks, too small to see, governed not by the neat predictability of Newton's clockwork, but by the shimmering probabilities of quantum mechanics. When two of these particles are created together, they can become entangled, their properties linked in ways that defy intuition. Spin one in a certain direction, and the other seems to know instantly, no matter how far apart they drift. Einstein himself struggled with this idea. He called it spooky action at a distance, because it seemed to mock the rule that nothing, not even information, can travel faster than light. To him, entanglement looked like a cheat, a hidden trick the universe must be playing to cover up some deeper, undiscovered mechanism. But experiments across decades, most famously in the late 20th century, showed that entanglement is no illusion. It happens. If you measure one particle, the other responds instantly, as though distance were irrelevant. From our perspective, it is as if the particles share a secret phone line that connects them faster than any signal could. Here, everyday life can help soften the strangeness. Imagine a pair of identical twins who have grown up together so closely that they finish each other's sentences. Place one in Paris and the other in Tokyo. And somehow, without phones or letters, each seems to know what the other is about to say. When one smiles, the other laughs. When one feels a chill, the other shivers. That is how entangled particles behave, not communicating in the usual sense, but existing in a state of togetherness that distance cannot dissolve. Still, there's a catch. While entanglement correlations appear instantaneous, they do not carry usable information faster than light. You cannot use them to send a message to Mars in 0 seconds or warn your past self of tomorrow's news. The trick lies in the randomness of quantum measurements. Each particle's outcome is unpredictable until measured. Only when the results are compared through ordinary slower-than-light communication do the correlations become clear. It's like receiving 2 envelopes in the mail, one in London, one in New York. Neither person knows what's inside until they open them, but when they finally compare notes, they discover the contents match perfectly. The envelopes seemed linked all along, but no letter travelled instantly between them. The connection was written in from the start, and yet, even with this limitation, entanglement feels deeply profound. It hints at a universe where separation is not as absolute as we think, where 2 things can remain part of one story, no matter how far apart they drift. Some physicists even speculate that entanglement is not just a curiosity, but the very glue of space-time itself, the threads that weave the fabric of reality. For us, lying here in the soft quiet of night, entanglement offers a metaphor of connection. You may be far from a loved one, separated by oceans or time zones, and yet you feel their presence when you think of them. No signal passes instantly, and yet the bond is real. Entanglement, in its quiet way, reminds us that togetherness can exist even across unimaginable distances. It also shows us something important about faster-than-light dreams. Not every strange effect that looks instantaneous can be harnessed as a technology. Entanglement refuses to be turned into a tachyonic telegraph. It is a reminder that the universe, while generous in wonder, still guards its boundaries. The speed of light remains unbroken, even as entanglement dances right up to its edge, teasing us with its elegance. And perhaps that is enough. Not every mystery needs to be a tool. Some can simply be a story, a source of awe, a whisper that the universe is richer and stranger than we can fully grasp. Entanglement belongs in that category. Not a spaceship engine, not a cosmic shortcut, but a quiet reminder that we are all, in some sense, still connected. So, as you breathe gently and let your thoughts drift, picture those twin particles, spinning together though galaxies apart, responding as if they were still side by side. It is not faster than light travel, not tachyonic rebellion, but something softer, the universe reminding us that distance may be large, but connection is larger still. Most paths in life lead forward. You step out the door, walk to the corner, turn left, and eventually arrive somewhere new. But every now and then, a path curves back toward itself. A hiking trail may loop in a circle. A train line may return you to the same station where you began. These loops are comforting. They suggest that no matter how far you wander, you can find your way back again. Physicists, always curious, have wondered if time could do something similar. Could the universe itself allow a path through space-time that loops back to its own beginning? In the mathematics of relativity, such paths exist. They are called closed time-like curves, closed because they loop, time-like because they follow the flow of time as experienced by a traveller. Imagine walking forward, step after step, only to discover that your footsteps carry you back to the very moment you set out. It sounds like science fiction, and indeed it has fueled countless stories. A traveller climbs into a machine, sets the dial, and emerges in an earlier year. A message circles back to its sender before it was written. Entire plots unravel from this premise, but here, in the soft light of relativity's equations, closed time-like curves are not merely fantasy. They are mathematical possibilities, hiding in the folds of space-time-like trails we have not yet walked. One way to picture them is through the metaphor of a train track. Normally, a train leaves one station and arrives at another, but some tracks are circular. The train keeps moving forward, never reversing, yet eventually it returns to where it began. A closed time-like curve would feel the same, a continuous forward motion, yet one that carries you into your own past. Of course, this raises the familiar paradoxes. If you could meet your younger self, could you change what happens next? Could you hand yourself a note that alters your choices? Would the loop remain stable, or would it tear itself apart in contradiction? These questions keep philosophers awake at night, but here, under the slow rhythm of our story, they can be allowed to drift gently, like puzzles half solved and set aside for later. There is even humour in imagining such loops. Think of déjà vu, that strange sensation that you've lived this moment before. Perhaps it's the universe's playful hint that time sometimes folds back on itself, giving us a fleeting glimpse of its circular structure. The feeling might be an illusion of the mind, but it echoes the deeper possibility of loops written into space-time's geometry. You might call it the cosmos's own version of a joke, repeated so often it feels familiar. And yet, closed time-like curves also carry a quiet beauty. They suggest that time, which feels like a strict arrow, may be more flexible than we think. Perhaps beginnings and endings are not as far apart as they appear. Perhaps stories do not only march forward, but can circle gracefully like rings spreading on a pond. Some solutions to Einstein's equations even describe entire universes built on loops. The physicist Kurt Gödel, better known for his work in mathematics and logic, proposed a rotating cosmos in which time itself might allow circular journeys. His model does not match the universe we see, but it stands as a reminder that relativity's rules are broad, wide enough to contain possibilities stranger than we dare imagine. To ground the thought, imagine sitting on a train that glides smoothly around a circular track. The scenery changes, the people come and go, but eventually you find yourself back at the same station. Time might feel like that if closed loops were real. Each moment flows forward, each tick of your watch continues, and yet, after enough turns, you might look up and realize you've arrived where you began. Would such a loop destroy free will? Or would it simply give life a different shape? Perhaps your choices would still matter, carving unique paths within the loop, even if the overall journey repeats. Perhaps, like a song played on repeat, the melody remains the same, but the experience shifts each time you hear it. For now, these ideas remain purely speculative. No experiment has found evidence of closed time-like curves. The universe we observe seems committed to its arrow of time, but letting your thoughts wander through the possibility can be soothing in its own way. It suggests that time is not a rigid corridor but a landscape, with valleys, hills, and perhaps the occasional circular path. So as you settle deeper into rest, imagine a train track beneath the stars curving softly through the cosmos. You ride it without hurry, watching galaxies drift by. The track bends, loops, and eventually carries you back to where you began, not in contradiction, but in completion, like a dream that circles back to its opening scene. Dreams of tachyons and warp bubbles are enticing, but science is not built on dreams alone. It leans on experiments, on observations, on the patient collection of data. If faster-than-light phenomena were hiding somewhere in the cosmos, surely the universe would have left us a clue by now. So far, though, every test whispers the same answer. Light remains supreme. One of the most striking confirmations comes from something you carry in your pocket almost every day: your phone. The global positioning system relies on satellites orbiting high above Earth, each carrying precise atomic clocks. These satellites must account for both special relativity, which slows their ticking because of speed, and general relativity, which quickens their ticking because of altitude in Earth's gravitational field. Without correcting for these effects, your GPS location would drift by miles within hours. The fact that GPS works so reliably is proof that Einstein's rules about light's boundary are woven into the very fabric of technology we trust each day. Beyond Earth, astronomers test these limits on cosmic scales. The Event Horizon Telescope, which produced the first images of black holes, relied on light signals captured from across the globe, combined with extraordinary precision. If tachyons or faster-than-light particles were involved, the timing would not have matched so perfectly. Yet it did, down to the tiniest fractions of a second. Light's loyalty held steady, even at the edge of space-time's most extreme environments. Then there are gravitational waves, ripples in space-time itself, first detected by the LIGO observatories in 2015. When two black holes collided more than 1 billion light-years away, the waves they sent arrived on Earth travelling at, you guessed it, the speed of light. Scientists checked carefully for any sign that the waves outran or lagged behind photons, but they found none. Once again, the cosmic speed limit held firm. Closer to the laboratory bench, physicists have searched for tachyons directly, particle accelerators, where protons smash together at nearly light speed, provide fertile ground for testing. Detectors are designed to pick up any hint of particles arriving faster than they should, or signals out of order. None have been confirmed. The swift ones, if they exist, remain silent. There was even a brief moment of excitement in 2011 when an experiment, called Opera, based in Italy, reported that neutrinos might have arrived slightly faster than light. For a few weeks, the physics world buzzed with possibility. Could this be the long-awaited evidence of superluminal particles? But science is cautious, and repetition is key. Other experiments checked. Errors were found. A loose cable, a miscalibrated clock. Once corrected, the neutrinos behaved properly, travelling just under light speed. The dream dissolved, but it left behind a valuable lesson. Extraordinary claims demand extraordinary care. And so for now, tachyons remain creatures of theory, not experiment. That does not make them worthless. Speculation can be a compass, pointing us toward new questions. But the compass must always be tested against the map of reality, and the map so far shows no signposts marked faster than light. It might feel disappointing, like waiting for a letter that never arrives. But there is comfort in this steadiness too. The laws of physics are reliable guides. They allow us to build technology, predict eclipses, understand the stars. Without that reliability, the universe would be chaos, and science would have no foothold. The fact that tachyons have not appeared may be less a loss than a reassurance. The cosmos, however strange, remains orderly. Still, one should not confuse absence with impossibility. The history of science is full of phenomena once thought unlikely, later confirmed. Gravitational waves, black holes, even quantum entanglement itself were once whispers on paper, before becoming experimental realities. Tachyons may never make that leap, but the door is not entirely shut. Each new detector, each new telescope, each new experiment is another knock on the door, another way of asking the universe, is there more to speed than light alone? So let your thoughts rest on this balance. On one side, the steady hand of evidence, GPS satellites, black hole images, gravitational waves, all confirming light's reign. On the other, the open hand of curiosity, theories that dare to imagine swifter messengers. Between the two lies the gentle truth of science, that it is both grounded and dreaming, both cautious and bold, and perhaps that is the most human part of this story. We test because we dream, and we dream because we test. Light holds the crown for now, but imagination keeps the contest alive. If you've ever seen photographs of the inside of a nuclear reactor, you may have noticed something almost otherworldly. A pool of water glowing with an eerie, shimmering blue light. It looks like something from a dream. Too bright, too unnatural, too beautiful to belong to the cold machinery of reactors and physics. Yet it is real, and it is one of the closest glimpses we have of what it means to outrun light. This glow is called Cherenkov radiation, and it appears when charged particles, electrons for example, race through water faster than light can move through that water. At first, the phrase may sound shocking. Faster than light? But isn't that forbidden? The answer lies in remembering that light's speed is not always the same. In a vacuum, photons travel at their ultimate limit, about 300,000 kilometers per second. But in water, glass, or other materials, they slow down as they interact with atoms along the way. It's like a runner weaving through a crowded street. Still quick, but not as swift as they would be on an open road. Electrons, meanwhile, are not slowed nearly as much by water. They can slip ahead, crossing the pool faster than light does within that medium. And when they do, they create a shockwave of light, an optical boom, much like the sonic boom made when a plane breaks the sound barrier. The result is that haunting blue glow, rippling softly through the water like a lantern lit from within. This glow is more than beautiful. It is also practical. Scientists use Cherenkov radiation to detect high-energy particles, to monitor nuclear reactors, even to study cosmic rays falling from space. It is a visible signature that something has outrun light's local pace, even if the cosmic speed limit in a vacuum remains untouched. To soften the strangeness, think of everyday examples of breaking barriers. When a jet flies faster than sound, we hear a boom, the air announcing its protest. When a boat moves quickly through water, waves spread outward in a V-shaped wake. Cherenkov radiation is the universe's version of these wakes, but made of light. The blue glow is space's own gentle boom. It's worth noticing how delicate the distinction is. These particles are not truly faster than light in the ultimate sense. They have not defied relativity. Instead, they have slipped past light's slowed pace in a medium. The universal speed limit still stands. It's just that the road inside the water is narrower, crowded, easier to outrun. The cosmos keeps its rules intact, even as it gives us glimpses of what it would feel like to see them bent, and what a glimpse it is. Picture standing beside one of those reactor pools in the quiet, the hum of machinery around you, the water still and radiant with its ghostly light. It's a reminder that physics is not always abstract. Sometimes it paints beauty right before our eyes, beauty that is as calming as it is strange. In a way, Cherenkov radiation gives us a metaphor for tachyonic dreams. We long to believe we could go faster than light, to streak across the stars without delay. And while the true cosmic limit has never been broken, the blue glow is a hint of how the world might look if it were possible. A softened promise, a quiet stand-in for the impossible. It also reminds us of something comforting. Nature is generous with wonder. Even when forbidding the grandest leap, it offers us smaller glimpses, like stepping stones across a stream. We may not walk beyond light speed, but we can see its echo in a blue shimmer, hear its cousin in a sonic boom, feel its metaphor in the waves trailing behind a boat. These are the universe's gentle ways of showing us what lies at the edges of its rules. And so, as you breathe slowly tonight, imagine that blue glow shimmering around you. Let it drift like a nightlight, soft and steady, reminding you that the laws of the universe, while firm, are not cold. They are capable of painting beauty in their limits. The glow is not a rebellion against physics, but a celebration of it. The quiet song of particles reminding us how close we can come to the edge, and how luminous that edge can be. If you've ever sat in a darkened room with a candle or a flashlight, you've probably noticed how quickly shadows can move. Sweep the light across a wall, and the shadow of your hand seems to leap instantly from one side to the other. In fact, if the wall is far away, the edge of that shadow can appear to slide faster than light itself. It's a playful trick of geometry, an illusion of speed that looks rebellious but is, in truth, perfectly obedient to physics. Let's picture this slowly. Imagine shining a laser pointer at the moon. As you sweep your hand back and forth, the red dot could dance across the lunar surface at unimaginable speeds. The moon is nearly 400,000 kilometers away. A small flick of your wrist might send the spot racing thousands of kilometers in a fraction of a second. If you calculated the apparent speed of that dot, it could easily exceed the speed of light. Yet nothing physical has actually moved across the moon. No particle, no photon, no bit of information has leapt ahead. The light rays are still leaving your pointer at light speed. The spot is simply the intersection of those rays with the surface, a shifting overlap that can slide as quickly as geometry allows. The same goes for shadows. When a spotlight sweeps across a mountain, the shadow of a cloud might seem to dash across the valley below faster than any jet. But again, no substance has travelled. The molecules of air, the particles of dust, the mountain itself remain still. Only the outline, the absence of light, has shifted, and absence cannot carry a message. This distinction may feel subtle, but it is deeply important. For faster than light travel to matter, something real must move: energy, matter, or information. Shadows and spots are not carriers. They are coincidences, places where paths cross. They can appear to move faster than light precisely because they are not bound by the responsibility of carrying anything. They are like silhouettes in a puppet show, sliding gracefully across the curtain, no matter how quickly the puppeteer moves. Everyday life offers more analogies. Imagine sitting in a theatre, watching the beam of a lighthouse sweep across the sea. The bright path of light seems to spin quickly, painting the horizon in a few seconds. If that horizon were far enough away, the beam's edge would sweep across at faster than light. Speeds. But of course, the lighthouse isn't breaking physics. It's simply rotating steadily, each photon moving outward at its lawful pace. The illusion is the movement of the intersection, not the actual motion of light. There's gentle humour in this. The universe teases us with sights that look like rebellion but aren't. It's like watching a magician pull a coin from behind your ear. You know it's a trick, but you smile anyway. The cosmos gives us these visual illusions, shadows dashing, beams racing, not to deceive us maliciously, but perhaps to remind us that perception is not the same as reality. And in truth, this is comforting. If shadows really could carry information faster than light, the world would collapse into paradoxes. Causes would lose their order, effects would leap ahead of their reasons. By making sure shadows remain only illusions, the universe preserves its consistency while still allowing us a taste of the impossible. In physics, such distinctions help sharpen our understanding. Scientists often use these illusions as teaching tools, showing students how easy it is to confuse appearance with reality. A shadow racing across the moon is dramatic, but it is harmless. It teaches us the difference between what looks fast and what truly is fast. And in that difference lies the heart of scientific clarity. But beyond the lessons, there is poetry too. Think of a night when you walked beneath street lamps, your shadow stretching far ahead. Perhaps it looked like another traveller, striding before you, arriving at corners before you reached them. In some sense, your shadow was a companion moving faster than you could ever hope to. Yet it carried nothing of you except your outline, a hollow reflection that could not speak, touch, or change the world. That is how these illusions live in our universe, companions of light, dancing along walls and valleys, giving us glimpses of impossible speed without ever letting us grasp it. They are playful hints of what it would mean to escape the light barrier, but also reminders that true motion is far stricter, bound to causality's steady rhythm. So as you settle deeper into quiet, picture a flashlight beam sweeping gently across the ceiling. The spot drifts, then slides more quickly until it seems to leap from one corner to another in an instant. Let it be a soothing thought, not a paradox, a simple illusion, a soft dance of geometry, a reminder that speed is not always what it seems. The shadows may run ahead, but the universe keeps its promises, and in those promises, steady, consistent, reliable, lies a beauty just as deep as any dream of breaking them. Science often begins not in laboratories, but in daydreams. A person sits by a window staring at the horizon and wonders, what if? What if we could breathe underwater? What if we could soar through the sky like birds? What if we could cross oceans in hours instead of months? These questions, once dismissed as impossible, eventually became everyday realities. Think of Jules Verne writing in the 19th century. His stories spoke of submarines that could roam beneath the waves, long before technology caught up. He described journeys to the moon, long before rockets existed. To many of his readers, these were fantasies, entertaining, but unlikely. And yet today we know nuclear submarines glide silently through the deep, and astronauts have walked across lunar soil. What was once imagination became history, or consider the airplane. At the turn of the 20th century, the idea of heavier-than-air flight was often ridiculed. Learned men declared it absurd, a waste of effort. Yet only a few years later, the Wright brothers lifted their fragile machine into the sky, wobbling but triumphant. From that small leap, entire industries were born. Today, we board airplanes with barely a second thought, sipping coffee as we cross continents that once took months of perilous sailing. These stories remind us that impossible is often just a placeholder, a word we use when the tools of today cannot yet grasp the dreams of tomorrow. The boundary between fantasy and science is porous, shifting with each generation. Tachyons, warp bubbles, and faster-than-light travel may sound fantastical now. They live mostly on chalkboards, in novels, in late-night conversations. But so too did submarines and rockets once live only in imagination. Whether tachyons will ever step from theory into reality, we cannot know. But the act of imagining them already shapes our science. It stretches our thinking, forces us to test boundaries, sharpens our understanding of why the speed of light is sacred in the first place. There is another layer to this. Imagination does not just inspire technology, it comforts us. To picture yourself slipping instantly across the stars or receiving a message from tomorrow is to indulge in a kind of cosmic storytelling. It reassures us that limits may not be final, that the universe may still surprise us. In this way, the impossible is not a wall, but a canvas, waiting for us to paint our questions upon it. Everyday life mirrors this in small ways. Think of a child staring at a cardboard box and declaring it a spaceship. The box remains cardboard. Yet for the child, the dream is real enough to inspire joy. Adults do the same, though our cardboard is mathematics, our crayons are equations. We imagine tachyons and warp drives not because they are here, but because pretending they might be helps us stretch toward understanding. There is also a deep patience in this process. Jules Verne never saw submarines built to his specifications. Leonardo da Vinci sketched flying machines centuries before the sky was conquered. Many dreamers plant seeds whose fruits they will never taste, but the planting itself matters. The ideas ripple outward, carried by others who refine them, who test them, who make them real. So tonight, let yourself dwell in that well in space between no and not yet. Imagine the impossible not as a failure of logic, but as a rehearsal for possibility. You may never ride a warp bubble or exchange letters with tachyons, but you can still take comfort in the fact that the act of wondering is itself a kind of discovery. Because in the end, the history of science is less a march of certainty and more a dance with the impossible. Each generation steps into the unknown, stumbles, laughs, tries again, and with each step the impossible retreats a little further until it becomes memory, then reality, then something so ordinary we forget it was once unbelievable. So close your eyes for a moment and imagine, what impossibility today will tomorrow's children take for granted? Perhaps one day they will tell stories of how their ancestors once believed stars were unreachable, just as we marvel that people once thought flight was fantasy. The impossible is always shifting, and in that shift we find both humility and hope. Stories have always been our way of exploring the impossible. Before we had equations to describe or experiments to test, we had tales told around fires, myths whispered to children, and books that invited us into other worlds. And sometimes these stories are not merely entertainment. They become metaphors for how the universe itself might work. One of the richest of these metaphors is the idea of the multiverse. It emerges from physics as a possible escape hatch from paradox, especially those caused by faster-than-light motion, or tachyons. If events can unfold in ways that seem contradictory, perhaps the universe avoids contradiction by splitting, branching into separate realities, where each possibility has a room to breathe. Think of it like a book that doesn't have just one ending, but many. You turn a page and see. If you choose the left path, go to page 47. If you choose the right path, go to page 82. Choose your own adventure books, so popular for children, mirror this structure. Each choice creates a new thread of story. None erases the others. They all exist, bound together by the same spine. In physics, this image takes shape in interpretations of quantum mechanics, such as the many-worlds hypothesis. Each outcome of a quantum event, each flip of a particle's spin, each roll of a cosmic die, spawns a new world, one where the coin lands heads, one where it lands tails. Both unfold, parallel and real, yet never touching. If tachyons or other faster-than-light effects threaten to create contradictions, the multiverse offers a poetic solution. Let each contradiction bloom into its own branch. Send a signal to the past warning of disaster. In one branch, the warning arrives and the disaster is averted. In another, the warning never comes and events unfold as before. Both are consistent because they are no longer competing in a single storyline. Everyday life gives us gentle echoes of this branching. Consider the decisions you make each day, what to eat, whether to call a friend, which route to take home. You can only choose one, but in imagination, all the other choices still feel alive. You can picture the meal you didn't cook, the friend you didn't call, the street you didn't walk down. In some sense, your mind already holds a multiverse of possibilities, even if only one is lived, and stories thrive on this structure. Films show us alternate timelines. Novels offer us parallel worlds. Sometimes they comfort us. The idea that in another universe, mistakes were avoided, loved ones survived, dreams were fulfilled. Sometimes they warn us that in another branch, the dangers we escaped became real. The multiverse becomes a canvas for all the what-ifs we cannot explore in one lifetime. There is something profoundly human in this. We long to believe our choices matter, that paths not taken are not lost but simply out of reach. We also long to resolve paradoxes, to avoid the knot of logic where something both happens and doesn't. The multiverse, whether real or metaphorical, satisfies both desires. It reassures us that contradictions can coexist, neatly separated into their own worlds, leaving our own consistent. Of course, scientists debate the reality of this idea. The multiverse remains speculative, not something we can yet confirm or deny. But its appeal lies not only in physics, but in philosophy, in storytelling, in the way it mirrors our own experience of life. We are always standing at crossroads, always wondering what might have been if we had chosen differently. The multiverse simply takes that wondering and turns it into cosmic architecture. So let your thoughts wander tonight as though you were holding such a branching book. Each turn of the page leads to another version of the story. In one, tachyons are real and communication is instant. In another, they remain myths, forever theoretical. In one, humanity crosses the stars on warp bubbles. In another, we remain earthbound, dreaming from afar. All stories unfold, each consistent within itself, each beautiful in its own way. And perhaps this is the truest role of cosmic storytelling. Not to declare one path correct and the others false, but to invite us to imagine them all, to see paradox not as failure, but as invitation, to remember that reality is larger than our single thread of experience. So close your eyes and picture a tree against the night sky. Each branch splits, then splits again, reaching upward and outward, until the canopy is a forest of stars. That tree is the universe's storybook, each branch a timeline, each twig a possibility. We walk one branch, but we can imagine them all, and in that imagining lies both peace and wonder. From the moment we take our first steps as children, we discover the joy of speed. A toddler runs across a room, laughing not because of where they're going, but because of how thrilling it feels to move quickly. The faster they go, the more alive the moment seems. That simple delight never truly leaves us. It grows into a deeper human urge, the desire to go faster, to push beyond limits, to see what lies ahead sooner than patience allows. Throughout history, this desire has shaped civilizations. Early hunters learned to tame horses, feeling the wind rush past as hooves thundered across plains. For centuries, a galloping horse was the pinnacle of speed, the benchmark against which all journeys were measured. Then came ships with tall sails, catching winds that could carry explorers across oceans. What once took years on foot could be crossed in months, then weeks. The pace of life changed with every new vessel. The Industrial Revolution brought trains that cut across landscapes with astonishing speed, their whistles echoing through valleys, their tracks stitching cities together like threads of steel. For the first time, ordinary people could travel farther than their ancestors ever dreamed, and do so in a single day. Soon after, automobiles gave individuals the power of speed at their fingertips. The open road became a symbol of freedom, and then, of course, came flight. What was once ridiculed as fantasy, humans soaring like birds, became reality with engines and wings. The Wright brothers' fragile craft wobbled across the sand dunes of Kitty Hawk, but it was enough to change the course of history. Airplanes grew larger, stronger, faster, until crossing oceans in hours became routine. The thrill of flight, once reserved for gods and myth, became a daily commute for millions. Yet, even that was not enough. Rockets soon followed, roaring through the atmosphere, carrying us beyond Earth itself. The first astronauts looked back and saw the planet as a blue marble, delicate against the blackness. It was the ultimate expression of humanity's hunger for speed, to leave home entirely, to cross not just oceans or skies, but the boundary of the world itself. And still, the stars remain distant. Even our fastest spacecraft crawl compared to the scale of the cosmos. Voyager 1, launched in 1977, has spent decades travelling, and only now drifts through the edge of interstellar space. It moves at tens of thousands of miles per hour, a pace unimaginable for a person, yet glacial against the canvas of light years. The human heart, restless as ever, asks, can't we go faster? This is where tachyons and other faster-than-light dreams enter the story. They are not just mathematical curiosities, they are reflections of our own longing. The thought of outrunning light, of stepping instantly across the galaxy, is not only about science, it is about us. It is about the part of us that runs for joy, that builds machines to break barriers, that cannot help but chase the horizon. Everyday anchors remind us of this urge. A child sprinting in a playground, a train racing across the countryside, a jet lifting from the runway, a rocket breaking free of Earth's pull, each is a chapter in the same story. The story of speed, of yearning, of the endless human desire to see what lies beyond. Perhaps tachyons will never exist, and faster-than-light travel will remain fantasy. But even if that is true, the dream itself is valuable. It pushes us to build, to imagine, to keep reaching. Without the dream of flight, there would be no airplanes. Without the dream of space, there would be no rockets. Without the dream of faster-than-light travel, perhaps we would never fully appreciate why light sets the rules at all. And maybe this is the quiet lesson. The desire to go faster is not only about distance, it is about curiosity, about hope, about refusing to accept that the horizon is the end. Whether it's a toddler running or a civilization building ships and rockets, the impulse is the same: to move, to reach, to discover. So as you rest tonight, think of yourself as part of this long story. You share the same heartbeat as the first runners, the same spark as the sailors, the same wonder as the astronauts. The tachyonic dream is simply the latest chapter in humanity's long conversation with speed. Whether it is ever realized or not, it is already meaningful because it is already part of us. And perhaps that is enough. To dream of going faster is to honor the part of us that longs to grow, to change, to see. Even if light remains the ultimate pace, our imaginations will always race ahead, leaving footprints on possibilities just beyond reach. Every dream, no matter how luminous, eventually comes to rest against the quiet wall of reality. For faster-than-light travel and tachyons, that wall is built from decades of careful measurement, experiments, and theory. And the consensus, at least for now, is clear. Tachyons remain speculative, unconfirmed, living only in the margins of mathematics and the pages of imagination. This doesn't mean they are meaningless. In fact, the history of science shows that even ideas that never become reality can still shape the way we think. They force us to test assumptions, to question what we thought was settled, to look for cracks in walls we once assumed unbreakable. Tachyons, like so many impossible concepts before them, are not failures of physics. They are sketches, unfinished, tentative, but valuable nonetheless. Think of an artist sitting with a blank canvas. Before the building is constructed, before the cathedral towers or the bridge arches across a river, there are drawings. The sketches may not resemble the final structure exactly. Some are discarded, some are refined, some remain only as curiosities in a notebook. Yet without sketches, no great work would rise. Science too depends on sketches. Tachyons are among them, lines drawn across the page of possibility, daring us to imagine what might exist beyond light's reach. The consensus tells us no evidence has appeared. Every test, from satellites to particle accelerators to telescopes peering into the depths of space, has upheld relativity's limit. Light and signals moving at its pace remain the fastest messengers of reality. And perhaps that is as it should be. If light did not hold steady, our universe might unravel into contradictions. But within that steadiness lies a paradox of its own. The very act of imagining beyond the limit strengthens our trust in the limit itself. When we test for tachyons and find none, we confirm the resilience of relativity. When we build detectors sensitive enough to catch impossibilities, and they return silence, we learn just how deeply the universe guards its order. Even the absence of discovery becomes a discovery. And yet, it is human to keep wondering. To think of tachyons is to practice curiosity. It is to remind ourselves that the universe is not closed, not fully known, not a finished story. Our greatest leaps have always begun this way, with someone daring to ask a question that seemed absurd. What if heavier than air flight were possible? What if invisible forces held the planets in orbit? What if time itself could bend? The answers have not always matched the dreams. Sometimes the dream survives only as metaphor. But that too has value. When you imagine faster than light travel, you may not build a starship, but you may glimpse the beauty of the laws that forbid it. You may notice the elegance of the light cone, the delicacy of causality, the way the cosmos balances freedom and order. So perhaps the boundary of possibility is not a wall after all, but a canvas, a place where we sketch, erase, and redraw, not to deny the limits, but to understand them more deeply. The act of sketching is itself a gift, the universe saying, go ahead, dream, see what happens if you push a little further. Tonight, as you lie in stillness, Think of yourself as both the artist and the audience. Before you is a blank page wide as the sky. You pick up the pencil of imagination and draw a line, faster than light, beyond the stars into a future not yet written. Whether that sketch ever becomes real is not the point. What matters is that you drew it, that you allowed yourself to wonder, that you joined the long tradition of humans daring to see beyond what is known. And in that, tachyons already serve their purpose, not as discovered particles, but as invitations. Invitations to keep sketching, keep dreaming, keep imagining the impossible until one day, perhaps, the impossible chooses to become real. And so, we have travelled together through cones of light and paradoxes, through the blue shimmer of Cherenkov pools, through tachyon dreams and warp bubbles and the strange whisper of entangled twins. We have wandered the edges of physics where speculation brushes against philosophy, where equations open into stories, and where impossibility becomes a kind of lullaby. If there is one truth to carry away, it is that the speed of light remains unbroken. For all our thought experiments, for all our sketches of tachyons and bubbles and loops, the universe has held its ground. Light continues to move at its steady pace, the patient courier of causality, the metronome of reality. It is a limit, yes, but also a gift. Without it, events would unravel into chaos and time itself might lose its meaning. And yet, even in the face of this firm boundary, we still dream. We imagine swifter messengers, instant journeys, glimpses of yesterday and tomorrow. These dreams are not wasted. They are the threads of curiosity that weave through science and storytelling alike. They remind us that human beings are not content only to live within limits. We lean against them, press our hands to the edges, and wonder what lies beyond. Perhaps that is why tachyons fascinate us. Not because we expect them to appear in a detector tomorrow, but because they embody a possibility that speaks to our hearts. They are symbols of freedom from delay, from distance, from the slow unfolding of cause and effect. To dream of tachyons is to dream of liberation from time's patient flow. But here, in the quiet of night, another perspective emerges. Maybe the speed of light is not a cage, but a lullaby. It slows the universe into a rhythm we can follow. It ensures that events arrive in order, that tomorrow is not already here, that the stories of our lives have beginnings and middles before they end. In this light, limits are not cruel, they are kind. They give us the chance to live each moment as it comes, unspoiled by knowledge of what's ahead. Free will, destiny, causality. These are heavy words, and they often weigh on our thoughts. But as you rest, let them drift like leaves on a river. Whether time is linear or looping, whether choice is absolute or harmonized with destiny, your experience remains real. The warmth of a blanket, the memory of laughter, the sight of stars. All of these are truths, no matter how the underlying fabric is woven. And so we come to the end of this journey. You might already feel your eyelids heavy, your breathing slowing, your thoughts drifting into places where paradoxes no longer matter. If so, that is perfectly fine. Sleep is its own form of time travel, carrying you gently forward without effort, delivering you to a new morning with no paradox at all. Before we part, let me offer you a simple invitation. Keep imagining. Keep sketching impossible ideas in the quiet corners of your mind. Even if tachyons remain whispers, even if light never yields its crown, your curiosity is its own kind of speed, the speed at which wonder travels, leaping across years, generations, even galaxies. Thank you for joining me tonight, for listening, for letting your mind wander through this dreamscape of science and story. Whether you're still awake or already drifting into dreams, know that you are part of a vast, gentle community of listeners, each in their own small corner of time, all connected by curiosity. And so, we close. Light continues at its steady pace, and we continue at ours. Somewhere just beyond that speed, imagination still waits, patient and shining. May you carry that glow into your sleep, into your tomorrow, into every quiet question you dare to ask. Good night, dear traveller. Sleep peacefully, wherever and whenever you may be,